let's start our seminar. And I suggest to solve some problems. First of all, devoted to tangents to parabola, and after them I try to explain how to obtain the equation for tangent line to the ellipse, and we consider some problem related to the properties of tangent line of ellipse. And let's try to solve the following two standard problems. In each of the following parabolas, show that P is the point on the curve which defines the equation, this equation, and find tangent and normal line to the parabola in this point. Any question maybe? And on the lecture we obtain the following two equations. First of them is the equation of tangent, and the second is the equation of parabola. And I recall that this equation to the point which coordinates x1, y1 to the parabola which defined by the equation y square is equal to px. In the first case, we have the equation in which the coordinate x is equal 9 y square. In the standard form, we have the equation y square is equal to px, and we must rewrite this equation in this standard form, and we obtain that y square is equal 1 divided 9 x. Easy to see, in this case p is equal to ratio 9. Oh, I'm sorry. The ratio 1 to 18. To p the ratio 1 divided 9, and we obtain that p is 1 divided 18. And let's check that this point, the coordinates of this point, satisfy to the equation x is equal 9 times y square. Easy to see, 9 is equal 9 times minus 1 square, and we obtain the equality. And we can assert that this point lies on this parabola. And after them, we can obtain the equation of the tangent as a normal line, substitute the given values of the coordinating parameter in the equation of the first tangent. We obtain y minus y1 is equal to the ratio p y1 times x minus x1. In our case, the coordinate y1 is equal -1 and x1 is equal 9, and we obtain y minus 1, y plus 1 is equal p, the ratio 1, 18, and this expression we can divide it. I'm sorry. Divided y1. y1 is equal minus 1, and times x minus 9, x minus 4. And we obtain the following equation x minus 9 plus 18 times y plus 1 is equal 0. X plus 18 y plus 9 is equal 0. We obtain the equation of tangent. Any question about this? Okay, the same way we can obtain the equation of the normal. Any question?
Did you yourself chose point 9 and -1?
By is given this coordinates is given.
Okay. Thank you.
Given. Yes, we have two expressions. The given the equation of parabola, and the point P is given, and we
thank you.
must to calculate the equation of tangent and normal in this point, in this given point. Yes. And the calculation for normal is the same, but in this calculation we change this parameter on the inverse with opposite sign. And after easy calculation, we obtain the following expression. We obtain the equation for normal. Tangent and normal. In the second case, the calculation is the same. On the lecture, we calculated we obtained the equation for the tangent, and for the normal, the calculation is the same as the previous case. In this case, we have that p is equal 6 and x1 is equal 1 divided 3, y1 is equal -2. And we can substitute these values in the second equation for the normal, and we obtain that y minus 2 plus 2 is equal minus 2 plus 2 divided 6 times x minus 1 divided 3. And we obtain that y plus 2 is equal 1 divided 3 times x minus 1 divided 3. Minus 1 divided. Yes, the question?
Yes, in the previous part, you wrote y minus y1 equals to p over y1. P is 1 over 18 and y1 is -1, right?
Yeah.
And
yes.
I think
x1 is equal, yes, 9, and y1 is equal -1. Minus 1 plus 1, yes?
But the fraction p over y minus 1, is it 18 or I think it will be...
This coefficient is a coefficient for the normal, and this for the tangent. This product is equal -1. And in this case, in one case, we obtain 18, and other case 1 divided 18, and in p is equal 1 divided 18, and y is equal -1, and one the case this coefficient is equal -18, another case is equal 1 divided 18.
But you write 18 there.
Let's check the signs. This one is equal -1 divided 18, and the second case for the normal, this coefficient is equal 18. This one is equal minus y1 divided p.
Okay, thank you.
This coefficient is for the normal.
Yes, it's
normal y. And in our case, the calculation is the same, and after simplifications, we obtain the following equation: 1 minus 1 divided 3x plus y plus 2 plus 1 divided 9 is equal. We can simplify this equation and rewrite in the following form. Let's multiply on the 9 left side, and we obtain minus 3x plus 9y minus 19 is equal 0. The equation of normal. For this case. Any question to understand the solution? is very, very simple task. We substitute the values of a given parameter in the equation of the tangent and normal line. And let's consider the equation of tangent for the ellipse. I very briefly explain how to obtain this equation for ellipse. We have the same reasoning, and we obtain the same way as in the case of parabola, the equation for the tangent for ellipse. We have some equation of ellipse, x squared divided a squared plus y squared divided b squared is equal 1. And we have some point P, x1, y1, and other point Q, which goes to the P. Q has coordinates x1 plus h1, y1 plus k. And we suggest that h and k is enough small numbers. And if we moved Q such a way that Q goes to P, the line second, which passes through these 2 points P and Q, tends to the tangent. And tangent is a limiting position of this second when Q goes to P. And as a case of the parabola, we can calculate the angle coefficient M as limit of the ratio K to H when HK tends to 0. And we suggest that both of these points P and Q belongs to our curves, and its coordinates satisfy the equation of our ellipse. And we obtain, maybe let's rewrite this equation in the following form: x b squared times x squared plus a squared y squared is equal a squared b squared. And as P belongs to our ellipse, the coordinates of these points are satisfy the equation of ellipse, and we obtain the equality b squared x1 squared plus a squared y1 squared is equal a squared b squared. In the same way, we obtain that b squared times x1 plus h squared plus a squared times y1 plus k squared is also equal a squared b squared. And subtract from second equation first equation. After subtraction, we obtain the following equality: b squared 2x1h plus h squared plus a squared 2y1k plus k squared is equal 0. And after simplification, we can rewrite this equation as k times a square to y1 plus k, and this first summons we can rewrite in the form b square h to x1 plus h. And let's change, rewrite previous equality in this following form, and from last equality we can express the ratio k to h, and we obtain that k divided h is equal minus 2 x1 plus h times b square h divided a, I'm sorry, b square to x1 plus h divided a square times 2y1 plus k, and opposite sign. And we can consider limit of the left and right side. H k goes to 0 by definition of limit, and in the limit we obtain the following equality: b squared times x1 divided a squared times y1, and this angle coefficient m. And easy to see the equation of the tangent in the general form is the following: y minus y1 is equal m times x minus x1. And we can substitute this expression for m to this equation. And after substitution, we obtain the following equality: y minus y1 is equal minus b square x1 a square y1 x minus x1. And we can write this equality in the following form: I square I'm sorry, result square y1 I square y1 times y minus y1 plus b square x1 times x minus x1 is equal 0. After simplification, we obtain the following equality: I rewrite the last equality on the central blackboard. And we obtain the following equality for the tangent. A square y1 square times y minus y1 plus b square x1 x minus x1 is equal 0. And we obtain the following. The following equality: a square y1 y minus y square minus a square y1 square plus b square x1 x minus b square x1 square. And we obtain the final expression from equation of ellipse. The last equation is equal a square b square. Final expression has the following form. If we divide it left side on the right side, we obtain the following formula: y1 y divided b square plus x1 x divided a square is equal 1. And in this form, and we obtain the following equation: x1 divided a square plus y1 divided b square is equal 1. Tangent. The equation for tangent for ellipse. Tangent. And we obtain the exact value for coefficients, and in this form, the tangent equation for ellipse is the following: y minus y1 is equal minus b square x1 a square y1 times x minus x1 tangent. And the normal has the following equation: a square y1 divided b square x1 times x minus x1. Normal. Normal equation. Any question, maybe? We need in the following expression the two forms of the tangent equation. In the form, easy to see that this form is the same for the equation for the ellipse. But in the equation of ellipse, one of the variable we change on the point of the coordinate of the point in which we consider the tangent, and the same form as the form for parabola. And the second form is standard form of the curve which passes through point from coordinates x1, y1, and has the angle coefficients which is equal m. And in the case of tangent to the ellipse, this angle coefficient is equal to the ratio minus b square x1 and a square y1. Easy to see that if we moved our ellipse, the angle coefficient is negative, and easy to see that if we moved if we have both coordinates of the same sign, in this case and in this case, the angle, the slope of this curve is negative. But if we have the opposite signs of the x and y, the slope is positive in two cases. And this observation is agree with our formula. Okay, we have the equation for the tangent and normal, and we can try to solve other problem. First of all, I suggest to solve enough simple problem which connected with tangent to the ellipse. Namely, I suggest consider the following task. Problem 2. Find the equation of those tangent to the ellipse, 7x squared plus 3y squared is equal to 28, which have the slope 2 divided 3, and also find the point of contact, the tangent and the ellipse. And intercept of x or x. Easy to see that if we fixed the slope, we obtain 2 points in which such tangent contact with the ellipse. For example, let's consider we have ellipse is some curve which has the fixed slope, and we can move this curve, and in this moment this curve contact with ellipse in some distinguished point. And after that we can continue to move this straight line. We obtain the symmetric point in which the straight line is fixed with given slope also contact with our ellipse. And this picture can be say us that we must obtain 2 points in which this tangent line contact with our ellipse. How to obtain? How to obtain this point of contact, and how to obtain the equation of the tangents. We have the must expression for the slope. Slope m is equal minus b square x1 divided a square y1. And this equation says us what the value of the a and b in this equation. We can rewrite this equation in the following form: x squared divided the ratio 28 and 7 and is equal 7 plus y squared divided 28 divided 3 is equal 1. And we obtain that a square is equal 4, b square is equal ratio 28 and 3. And given that m is equal 2 divided 3, and if we substitute these values in the expression for the slope, we can obtain that the ratio y1 x1 is equal minus b squared divided a square times 3 divided 2. B square 28 divided 3, a square is equal 4 times 3, 2. We can subtract 3 and we obtain that the ratio is equal minus 7 divided 2. Let's check. 14 divided 4, 7 divided 2, minus 7, 2. And we obtain that y1 is equal minus 7 divided 2 times x1. Yes, the question? Any question? Do you understand this calculation? We calculated the ratio y1 and x1, and after that we can exactly calculate the values of this for these coordinates. We can substitute this expression in the equation of the ellipse. After then, we obtain the following equation: 7x1 square plus 3 times minus 7 divided to x1 square is equal 28. 7x1 square plus 3. Oh, wait, I'm sorry. Okay. Easy to see this equation, this expression is equal 7 times 4 square, and this
Sorry, Professor.
Okay. The question is,
why is it 147 x1 squared? I think it should be the. Oh, okay. So.
It's right, eh?
Yeah.
It's
okay.
Yes. Let's check our calculation. We can subtract, and x1 is equal 4 divided 5, and y1 is equal minus and minus 14 divided 5. Is only one point, and other point is same absolute values but with opposite sign, plus minus. And second point, second coordinates y1 has that also to value minus plus, and we obtain 2 points. 2 points of contact. First of all, point P1 has the coordinate 4 divided 5, and second minus 14 divided 5. And second point, P2 has a coordinate minus 4 divided 5 plus 14 divided 5. We have 2 points. And in this point, the slope is equal 2 divided 3. 2 divided 3. And we obtain the following equation for tangent y minus y plus is equal to 2 divided 3 x minus. And the second tangent y minus 14 divided 5 is equal 2 divided 3 times x plus 4 divided 5. Two equations for tangent. And the same way we have two equations for normal. For normals. Y plus equation. And we can also to find the point of intersection of our tangent with x with x O x. The symmetrical axis. Let's find first of this. Let's put y is equal to 0 in this equation, and we obtain that the ratio of 14.5 is equal and we have the point intersection 5, 0, and this point minus 5, 0. T1, T2 minus 5, 0. Intersection points with OX. Question maybe? Okay. Also enough enough easy task. But in this case, we need to find the point of contact. We have the exact value of slope and try to point of contact. We can see that these points are not defined uniquely. We have 2 points, and this draw illustrated this fact. If we fixed the slope of tangent, we have exactly 2 points in which this straight line is given slope.
I'm sorry, Professor.
Contact is curve. Yes.
Point of contact for what? I don't understand the question. Point of contact.
Contact this point, which this point is common for our tangent and the curve.
The tangent and the ellipse, right?
Yeah. I have the sum straight line. This equation of this straight line fixed only a slope of this. This straight line has a general form: y is equal to k times x plus b. B is parameter. X, the slope. The slope k is fixed and given, and we must find the point of contact, exactly the point in which the tangent has the same slope as given. And the idea, we have the formula for the slope of tangent, and this formula is the following form, and the equation of ellipse is given, and we have the exact values of b and a, and the exact values of b squared and a squared, and we can exactly find the ratio, the coordinates of this point. First and second coordinates, the ratio. But if we know this ratio, we can substitute the equation with related these coordinates in the equation of the ellipse. And after this substitution, we obtain equation which define the exact value of these coordinates. We have quadratic equation, and therefore we obtain 2 values for each coordinate, and we obtain 2 points. And this picture illustrated this idea. If you have the family of the straight line, which all of them have the same slope, and we can choose from these values to tangent for our ellipse. We have infinitely many straight lines. We can move this straight line parallel one to other, and moving the straight line, we find the point of contact with straight line with ellipse. Only 1 point. This point in which this straight line became tangent to our curve. And this picture shows us that we have only two points. If we change the slope, we obtain the values of slope, and for every value of the slope we can find only two positions of the straight line from this family in which this straight line became tangent to our ellipse. And this calculation illustrated this simple geometrical idea. Any question maybe? Do you understand? Okay. We try to solve one more problem. The following task. Problem 3. Find equations of straight lines that are tangent to the ellipse x squared divided 18 plus y squared divided 8 is equal 1, and pass through the point minus 6, 1. In this case, we haven't the value from the slope, but we have exactly point which belongs to our tangent. We have the general equation for the all tangent to our ellipse. The general form is tangent is following: x1 a square plus y1 divided b square is equal 0. This equation help us to find the exact values of tangent point for point in which we have this equation for tangent. This general formula for all tangent straight line, but our tangent, which we must to find from this condition, pass through the point which has the coordinates minus 6, 0, and therefore these coordinates satisfy this equation. In this equation, a square is equal 18, b square is equal 8, and we obtain the following relation between coordinates of point P. we have the infinitely many tangent straight line. And we have some points on the plane. Point M1, which has the coordinates -6, 0. In one of these tangent pass from this point. And we must find the equation of this straight line. If we substitute these values from this equation, we must obtain the equality. And we obtain the following equality: -6 divided 18x plus y1 times 0 is equal 1. Easy to see that from this equation we obtain that x1 is equal -3. x1 is equal -3. And if we know that one of the coordinates of the point of the ellipse, we can find other coordinates from the equation of ellipse. And we can substitute these values from the equation of ellipse. After substitution, we obtain the following equality. -3 square divided 18 plus y1 square divided 8 is equal 1. Easy to see that y1 square divided 8 is equal 1 divided 2. y1 square is equal 4. And y is equal plus minus 2. And we obtain 2 point of contact of two straight line, which defines this condition. First point P1 has the coordinate 2, 0. Second P2 has coordinate -2, 0. And I'm sorry. -3 plus 2 minus 3 minus 2. -3 minus 2. Because point lies on this axis OX, we have exactly 2 point of contact, and this tangent are symmetric relatively axis OX. And we can exactly calculate the equation for this tangent straight line, and we have the following equation: x times minus 3 divided 18 plus y 2 plus minus divided 8 is equal 1. We can multiply. Left side from. We can multiply left side on 36. Oh no, 36. 72 maybe. Oh, sorry. 36, exactly 36. And we obtain minus 6x plus minus 9y minus 36 equal 0. We have two tangents and 2 points. Point of contact, this tangent and our curve. Any question about this problem?
Professor, the point M is not on the ellipse, right? The point M, which was given in the question.
Point M?
Minus 6 and 0. Minus 6 and 0. In the question.
Yes. This point is the point which lies on our tangent. This point is given.
But it's not on the ellipse, right? It's not on the ellipse.
Why? What mean even? It's not essentially even. Not even. We can fix any point.
Okay. Yes.
We can any point. This is not essentially even, not even. We can consider arbitrary point on the plane. Easy to see.
Okay.
Okay. Well, easy to see. What we have ellipse and we have any point, and we have infinitely many straight lines which pass through this point, and this straight line have various slope, and we can change slope and see then this straight line contact with our curve in one point, and in this moment we obtain the tangent. We change the slope and rotate this straight line, and this straight line in one moment meet our curve in one point. This point of contact, and in this moment this straight line from our family became the tangent to our curve. We also change the slope and find other point in which also the straight line from our family meet our curve. And we obtain 2 point and 2 tangent. In this concrete case, this point M1 has the coordinate minus 6, 0. It's arbitrary coordinate.
I understand.
But in this case, the tangent has some distinguished form. This tangent asymmetric on the axis. Only in this case. In arbitrary case, it's not so. Okay, do you understand, yes?
Yes, thank you.
Okay. And let's continue, and we have 5 minutes or 10. So, sorry. Okay, have enough time. Okay, let's consider more complex problem, but I'm not sure that we have enough time to solve this problem, but we can start to solve. Most complicated problem from our list. Problem 4. Maybe. Okay, maybe solve less hard problem. Find points. That's okay. Find the equations of common tangent to 2 ellipses. One of them has the equation x squared divided 20 plus y squared divided 5 is equal 0, and second has the following equation x squared divided 80 plus 4y squared divided 5 is equal 0. Easy to see if we have, for example, the following ellipse. We can to find the common tangent to this ellipse is tangents essentially different from this ellipse and from this. But in this case, easy to see, we have the following values for parameters a and b for the first ellipse and the second ellipse. For the first A is equal root square 20, B root square 5, A1, B1. For second ellipse, we have A2 is equal root square 18, B square root square 5 divided 2. Exactly 2 root square 5. In this case, 4 root square 5. Root square 5 divided 2. And we have the following picture for this problem. Let root square 5 exactly 2.2. And this distance is twice this distance. And this distance is twice this. Is twice this. And we have this ellipse. And easy to see, in this case, we can find the 4 various tangent straight line to this ellipse. And we must find the exact equations for this tangent. How to solve this problem? We have two family tangent line. One of them, the family of tangent to the first ellipse, and second family, the family tangents to the second ellipse. The first family has the following equation: x1 divided a square 20 plus y1 divided is equal 1, and second x2 divided 18 plus y2 divided the first family has as parameter the coordinates of the point of contact, tangent and curve, and we have the same parameter for the second family. If we have common tangent to other curve, this common this tangent must pass through the point contact of the which has the coordinate x2 and y2. The point of contact, this tangent, is the second curve. So we obtain the following system equation: x to x1 divided 2 plus y to y1 divided 5 is equal 1. And the second, x to x1 divided 18 plus 4 y to y1 divided 5 is equal 1. We have this for this linear system equation relatively the product x to x1 y to y1. Let's denote this u2, this u1. We have new unknown variable, and we have linear system, and we can define these values to solve this linear system. We obtain the following system: u1 plus 4 u2 is equal 20, u1 plus 64 u2 is equal 80. We can to solve this system, and we obtain 60. We can subtract them from the second equation, first equation, and after subtracting, we obtain 60 u2 is equal 60. u2 is equal 1. u2 is equal 1. u1 is equal 16. We have two products, x2, x1 is equal 16, y2, y1 product is equal 1. We have two relations between unknown coordinates of point contact for the first and second curve. And I haven't any time, but I give the plan to solve this problem, and I hope that we finished the solution on the next seminar. We have one relation between these coordinates, and we have also the same equation for this curve. If we have the general curve, we have the one equation which has the two various forms, and we can use this observation. Easy to see that this and this point also we have two various ways. First, in my opinion, more simple way, use this equation in this form. We can substitute in this equation, the second relation between we have the following equality: x2 is equal 16 divided x1, and y2 is equal 1 divided y2. If we substitute this equation in the next curve, and we have the same equation for the we have two canonical equation for the same curve, and we obtain relation between the coordinates x1 and x2, and we can write this equation relatively x1. We obtain quadratic equation and obtain the values for two values for x1 and two values for y1, and we obtain the values for 4 point of contact. I have any time, and this problem will be a home task, and I hope that on the next seminar we finished this solution. Thank you for attention.